So good afternoon, I'm Arvind Kumar, and I will be talking about a potential scaling path to an intelligent machine. And I understand this is the daring session, so I'm going to be pretty daring here, I hope. So I'd just like to thank my collaborators, especially Winfried Wilke, for letting me have the microphone this afternoon. And I would also like to thank the organizers and DARPA for the funding. So I think there's been a tremendous amount of talk already about what an intelligent machine is, so I don't think I need to dwell on what the characteristics of an intelligent machine are, but just to be very brief, we're really looking for a system which can learn continuously and in at least a semi-unsupervised way. That is, maybe with a little bit of hand-holding, that can predict patterns, detect when things are not quite right, and we have our eye towards eventually something that maybe can do some kind of a motor function to achieve its goals, and with an eye towards robotics, for example. So one of the sort of key differences between machine intelligence, which we view as the sort of the next big step, and machine learning, is really that machine intelligence is focused on the formation of new synapses, as opposed to just changing weights of existing synapses. And this is really central to the learning process, and particularly to the continuous learning that we had like to see as one of the major objectives of the machine intelligence. So design of an intelligent machine doesn't just mean scaling up the number of neurons and eventually the number of synapses, but also really means focusing on this big question of the massive interconnectivity. Because what we'd like to have is a plastic interconnectivity network, because physically we simply cannot afford to have a fully connected wired network, and therefore we have to be selective in the rewiring that we do, yet we'd like to have a flexible system in which we can rewire as the system learns. And this is what we view as the biggest challenge in designing an intelligent machine. So this is kind of a cartoon of what we think an intelligent machine would look like. We'd like it to be able to take a large number of sensory inputs, which could be very diverse in their forms. They could be audio, there could be news feeds, there could be satellite information, and then process that through some kind of a cortical learning engine. And in this case, we've shown this as a hierarchy consisting of a number of sequence memories. And each of these memories has connections within itself and processes the information. And the purpose of each of these various stages in the hierarchy is to take the information that's fed into it and then synthesize it into some kind of a stable representation, which is much more compressed or compact than the information that it was given, and then feed that up into the next level, into the hierarchy. And then the kind of desired outputs we'd like to have are, we'd like it to be able to be predictive, to recognize anomalies, and then to react in some way or another, and then, if necessary, change its own model of the world. So as you can imagine, this is the kind of thing that a human being does, and Mother Nature has given us a real abundance of neurons and synapses. So we would expect that if we were to try to realize this system in hardware, it's not surprising that we would be needing a lot in terms of resources. And there's this nice paper which summarizes a little bit why we need so many neurons and so many synapses. But because there are so many possible temporal patterns that could come from these inputs, when we have these thousands of neurons, and when we have so many neurons and so many synapses, this gives us the ability to really recognize robustly these patterns, even in the presence of a large amount of noise and variation. So as I said, Mother Nature has an incredible advantage over us. I took this plot, which really illustrates kind of Mother Nature's scaling law of synapses versus neurons. And it just shows how much ahead of the game Mother Nature is. Typically, the neurons have a fan-out of the order of 10 to the fourth. And while it's not a completely fair comparison, we can look at VLSI and say that, well, a transistor has a typical fan-out of 4, even though a neuron is in itself a complete computational unit, and a transistor may just be part of some kind of a computational block. And this illustrates this enormous kind of connectome gap between VLSI and a biological system. And also, on the other hand, you have machine learning, which often can have a fully connected system. And so we really have to think a little bit carefully about how do we want to implement a system like this in hardware. So resource virtualization also becomes an essential part in thinking about how to build a very scaled up system. So what are the requirements for a VLSI implementation? Well, we could try to store all of these synaptic connections in memory and just do it all in software. And if we think about a human scale system and sort of storing, of the order of 1,000 or 10,000 connections per neuron, we're talking about a lot of memory, but it's not something that's just inconceivable. It's in the 10 to 100 terabyte range. The second requirement is we can't operate on all of this in a very sequential manner, so we want to spread out and distribute. Perhaps use a large number in the thousands of simple processors in parallel. Each of these may be able to carry out some kind of a specialized task, yet we'd like to be able to be flexible in what we assign that task, and maybe the task that's assigned to each of the processors could be different, for example. So since the neural algorithms are rapidly evolving, we would like to have the flexibility in being able to perhaps change what that particular task that's given to a given processor might be. And another part that's very essential is that because we have such distributed processors with so many of them, they need to be able to talk amongst themselves, and this requires a very high communications bandwidth between processors, somewhere in the range of 10 to 100 gigabits per second. And then we want to do all of this and still at least do this with an acceptable power budget, which doesn't necessarily mean something that's ultra low power to start with, but something that could at least give us a proof of concept that you could actually do this and still manage to pay the bills and do this within a reasonable power and acceptable cooling budget. So I was going to talk about wafer scale integration. I was a little bit nervous about doing that because I thought that this is a very new concept, but I'd first like to thank very much Karl-Heinz for introducing and showing that this is actually feasible. It is possible to make an entire system on a wafer. And also there was a nice talk this morning by Joseph Bates, and he did also talk about how ideal and wonderful it would be if you could actually put all of these processors down on a single wafer. So again, the basic idea of wafer scale integration is to realize an entire system on a wafer using a full silicon wafer. We're using 300 millimeter wafers. You could use 200 millimeter wafers also. But not only that, once you've actually made an entire system on a wafer, you can scale the system by stacking. So what we do is use wafer-to-wafer bonding techniques and through stratum vias that connect these to connect multiple wafers in a stacked configuration. So this allows us to support very dense interstrata connectivity. The reason is that we can thin these wafers down, which allows us to preserve the aspect ratio of these TSVs. And when we do that, we can make these very, very dense. Now, of course, one cannot reasonably expect that everything is going to yield on a single wafer. In fact, this has been one of the major issues with wafer scale integration. So fault tolerance and repair techniques are really central to designing a wafer scale type of system. So just to show you that that's not just a cartoon, we are actually doing this at the IBM Albany Nanotech Center. Here's an example of 4 strata. And in this case, we have bonded together 300 millimeter wafers. The wafers have been thinned to 5 microns. And we have 2 kinds of TSVs in this picture, those that are within a stratum or those that connect from one stratum to another. And we get very dense pitches in the range of 1/4 to 1 micron inter and intrastrata copper TSVs. Actually, in his classic paper, Carver-Mead pointed out 2 potential very interesting technologies for neuromorphic computing. One of them is analog, and I know that there are lots and lots of groups who are already working on this, so we decided to look at the other one, which is indeed wafer scale integration. So what does 3D wafer scale integration really buy us? It buys us lots of memory that we can now put on a wafer instead of on a chip. Now, there's been a lot of talk about co-location of the processor and the memory, so this allows us to get the processor and the memory linked through a high bandwidth connection, which opens up the CPU to memory bottleneck. And third, we get a very high connectivity between these processors, which is useful for passing messages back and forth amongst them. So the biggest drawback really for wafer scale integration, or argument against it up to now, has been the fault tolerance. And for enterprise computing, this is a very natural issue to bring up because we really can't afford mistakes. However, cortical algorithms have a tendency to be far, far more resilient. This is an example of an HTM-like simulation. The y-axis here is the average reward. The x-axis here is the decision epoch. So this system was set, trained, and it was running along nicely. And then all of a sudden, somewhere here in the middle, either half or 3/4 of the columns were randomly damaged, removed from the system. And the system was, what we wanted to see was whether the system could recover. And so there is an initial dip here, an initial break, but then the system is able to retrain itself, and then it recovers to almost the same level that it did before. And this is one reason why we think that the resilience of these cortical algorithms makes this wafer-scale yield problems much, much less of a concern. These systems can tolerate having some defects, and they will continue to work fine. So in order to try to evaluate the prospects, we did a paper study, and I'm going to talk about that here. The purpose of the study was to really assess the feasibility of using 3D wafer scale integration for digital CMOS and for scaling up to large numbers of neuron count and connectivity. So in order to do that, we need some kind of a connectivity model, because we don't have a gigantic program somewhere that's running that takes all of these multisensory inputs and does all of this processing, and from which we can really evaluate. However, we do have something, which is we do know, at least partially, something about how the brain works. So we can make some kind of a connectivity model and use that as a basis to decide whether we actually have these kinds of capabilities in such a scaled-up 3D wafer scale system. So in order to do this scaling study, I took 3 examples. The first case I call a base case. Then I scale it up to a primate case. And then finally, I asked the question of, well, what happens if we try to scale it up to a human-level case? And the metrics that I want to look at are bandwidth, latency, and power. So in order to look at the connectivity, it's well known and was discussed in some of the talks yesterday that the brain has a very natural way of segregating itself into local connectivity, which is called gray matter, and global connectivity, white matter. And this is done in order to, we think, achieve very high interconnectivity within the brain, yet short conduction delays. There's a nice paper here that talks about this. And so, as I said, since we don't have really another big program, but we want to try to achieve a system which has the kind of functionality that we want to get from a brain, we can say, well, let's use this connectivity information to estimate the level of networking that's needed for brain functionality. So the connectivity model that we came up with looks something like this. It consists of regions which have gray matter, very dense connections within them. And then between these regions, we have white matter connections, which are much sparser. So the gray matter, again, corresponds to this local connectivity within a region. White matter is global connectivity between regions. So the model for the gray matter connectivity came out of studies that were done on rat brains. These are plots of the connection probability as a function of distance. It's generally found that the connection probability decreases as a function of distance, and these curves can be parameterized. Rather than focusing so much on a specific value for this, I would just like to say that what we do is we use a general model, and then we allow ourselves to say that, okay, there's some decay in the connection probability as a function of distance, and that decay can be characterized by some kind of a decay length. And in this case, it's typically in the hundreds of microns, but again, this is a parameter that could be potentially changed in the model. For the white matter, the global connectivity, luckily there exists a simple model, and this is based on the idea of a small world network. And I think this concept is probably familiar to most people. This is the concept in the sort of 6 degrees of separation, that if you look at all the people in the world and you start asking yourself, well, do you know somebody? Well, if you start looking at it through chains, you can see that typically we know each other through maybe 5 or 6 other people who know each other, who know each other, who know each other, who know each other. And the brain, actually, if you look at this mathematically, falls in the sweet spot of this curve, which I don't have a lot of time to explain, but the idea is that this is a sweet spot between having a completely regular network, which has a high degree of cliquishness. In other words, every neighbor seems to know each other, but it takes a very long time to go from one side to the other side in terms of the number of hops. And yet, on the other hand, or the other extreme is a random network in which neighbors often don't know each other, but it doesn't take very long. But there exists a fairly large regime that's right between these two, which still has a high degree of clickishness and yet has a short path length as measured by the number of hops it takes to go from one side or one node to another node. And this has been studied and is really an attractive model for the brain functional networks and has been observed in numerous brain studies. I added this at the last minute because I know this diagram has been shown. This wiring diagram for the macaque monkey has been shown repeatedly, and this is another example of a small world network. So the nice thing is we can go back into the literature, use this model, and actually take parameters from these various studies that have found that functionally the brain shows this kind of a small world network topology. The system we have in mind looks like this. It consists of a 3D stack. Some of the wafers are logic wafers, which means that they have thousands of processors on them. These processors are stitched together, so these aren't just traditional chips. They are tiled, and they're put entirely onto the wafer. And then we also have memory wafers, and these wafers provide the memory for these logic processors. This is a private memory, meaning that each one of these processors has its own memory domain. So some of the assumptions we used in the scaling study. For the memory wafer, I started with DRAM because it's a mature technology. And this means that on a 300 millimeter wafer at current densities, I can get about a whole terabyte of memory. And if I partition this into 1,000 sections, I can get 1,000 1 gigabyte sections. And I want to point out that this might be a little bit pessimistic because there are a lot of new emerging memories on the market, and these could potentially give us much greater densities on a wafer. But nonetheless, in the interest of sort of taking a worst case with current technologies, I have focused on DRAM in the study. A logic wafer, on the other hand, consists of thousands of these small processors. As I mentioned, they are stitched together. But we not only stitch together nearest neighbors, but we also have these express lanes. I've only shown one here for clarity, but the idea is that they are hardwired. However, they allow these hops to proceed at a much faster rate if we can put a few of these in, and that greatly reduces the potential latency by cutting the total number of hops that it's needed to go for communicating, say, between this node and this node, or perhaps this node and another node that might be on another wafer somewhere. Finally, we need to partition this. So what I've done is chosen to average about 1,000 synapses per neuron. This is in the human being range, but it's usually a little bit at the lower end. Somewhere the range that's usually quoted is between 1,000 and 10,000. And for reasons I can't really get into, you can use a compressed scheme for representing these connections, and that requires about 30 bits per synaptic connection. So at 1 gigabyte per node, each of these nodes could house about 250,000 neurons. And I've also had to make an assumption on sort of regionality. I've chosen to assume about 27 nodes per region, which means about 7 million neurons per region. This is an example of using this kind of a model. This is the local and global connectivity, the number of connections, versus the number of hops that are necessary to make that connection. Not surprisingly, the short-range connections, there are many more of them. That's an assumption here. We assumed that 90% of the connections in this particular case were gray, 10% were white. That's why you see there's much more area under this curve than under this curve. However, the latency is really set by the number of hops, and the fact that it still takes about between 20 and 25 hops for the farthest case will set the latency in the system. So we really have to pay attention to this tail, even though the majority of the connections are actually local. So here's the scaling study that I did, and we tried to get a wide range of intelligence, as you can see here. At the low end, we call this the base case. This corresponds to something like a small mammal at about 500 million neurons. In all of the cases, I've kept the number of synapses per neuron fixed at 1,000. The second case is a kind of a primate case, and a third case is scaling up to a human case. This is actually 30 billion, which is a little bit more than in the neurocortex, but less than in the total human brain. This is the total number of nodes that I would need, and this is the number of nodes I can put on a wafer. For this case, I put 1,700, and then in these cases, I'm kind of assuming that I can't put more than about 7,000 nodes onto a single wafer. And then I look at how many wafers do I need. So certainly, it's very reasonable to think I need 1 or 2. And 16 is not that much when you look at the fact that we have been able to do 4 in the past. And then how many memory wafers do I need if I want to maintain 1,000 potential connections per neuron. And again, for these two cases, it's still certainly very reasonable, 2 or 16. For the human case, I'm not going to stand here and try to tell you that I could actually put together 16 plus 128 wafers. That's too tall a stack. So some innovation would be needed on the memory level if we wanted to try to build this up to a human scale system. And I think I forgot to mention that each of these represents an 8x increase in the number of total neurons. So first we looked at the bandwidth, and here I've had to make an assumption about the activity factor. In this case, I chose it to be about 1%. The number of neurons, as I mentioned, is 250,000, and I've kept the average number of synapses per neuron at 1,000. And I've also had to make an assumption about how many bits there are per message. In this case, I've chosen the header and payload to be about 200 bits per message. And then I've looked at the bandwidth requirements for these three cases, and they fall in the range of a few tens of gigabits per second. And then I look at the actual wafer scale implementation where I can put dense wiring between the processors because this is silicon, and I run these at a certain frequency. This is the bus frequency. So in this case, I assumed about 2,000 wires and a bus frequency of 100 megahertz, which may seem slow. However, because we're now sending the signals in parallel, we have to be careful about things like skew, and therefore we can't raise this frequency too much. And if I compute this together, divide by 2, because I'm only looking at the outgoing bandwidth, it shows that I have a capability of about 100 gigabits per second per node, which is comfortably able to accommodate these types of bandwidth requirements. Next, I looked at the latency for these three cases. And as I mentioned earlier, we put in these express lanes, and they greatly help to reduce the total number of hops between processors. Here are the three cases: the base case, the primate case, the human case. And I'm assuming that we're now not in a bandwidth-limited case. And that's because we are comfortably able to accommodate what we thought were the bandwidth requirements from before. And the communications latency really depends on the number of hops. The blue is sort of the average latency, and the red is kind of the maximum latency, which for the human case is about 40. We can make a rough estimate of the worst case then based on this. For 40 hops and then about 100 nanoseconds per hops, this comes out to be in the range of a few microseconds, which can be hidden behind the compute cycle. A total compute cycle probably runs a few milliseconds. So if we're not really bandwidth limited, we can accommodate all of the hops that need to be done, the communication that needs to be done behind the compute cycle. Next, we look at the power. So this plot shows us the communication power in blue, the memory power in green, the computation power in orange, and then adding these up, the total power that's expected per node. So let me go through these a little bit step by step. For the computation power, we used some numbers I got from ARM-type cores, which are in the range of a few tens of microwatts per megahertz, which adds up to about half a watt per node at 1 gigahertz. For the memory power, using some standard data sheets for 1 gigabyte of DRAM, 1% activity factor, this is roughly in the range of 100 milliwatts. And for the communication power, we know what the bandwidth requirements are, but we now have parallel communication, which means we have to charge up a wire, and that charging cost is a half C capacitance of the wire, V squared per wire. And the x-axis here is the white matter fraction of the connections. I didn't have a really good answer for this, so that's why I left it as a parameter. I know that there are some estimations of this, but nonetheless, this is something that could probably vary a lot depending on the application. So I chose to just use this as a parameter and plot results as a function of that. Now, the important thing to notice here is that we're dominated really by the orange, which is the computation power, and not by the blue, which is the communication power. And this is because we've been able to use wires on silicon, which are low capacitance, as opposed to putting chips onto a board. So by comparison, if we were to use packaged chips on a board instead, then we could attain these kinds of bandwidths. The problem is that they could be done through SerDes, multi-gigabit transceivers, and that requires a very large power expenditure. So rather than having the communication power as being dominant, in this system, we've been able to reduce it significantly, and right now the dominant fraction is from the computation power. Now again, we've done this probably as a worst case scenario because we're using commercialized ARM processors. But if you were to really design the system and maybe use some of the tricks that have been discussed in this forum, you could actually reduce this significantly. So even this might be somewhat of an upper bound. So that brings me to a summary. So we've looked at these metrics, the bandwidth. So we feel fairly comfortable that we can accommodate the kinds of bandwidths that are needed for human brain functionality within the wafer scale integration and the ability to put a lot of wires down. The latency looks like it's in the microsecond range. This is something that could be hidden behind the compute cycle. The power estimate added up to something like in the order of 1 watt per node. Which includes the computation, the communication, and the memory, dominated by the computation. And then lastly, I wanted to just say something about the form factor, which if you stack up all of these wafers, it looks something like a pizza box, but then of course, we have to put I/O, cooling, power, and a power supply, so it's not going to be quite that simple, but nonetheless, it gives us something that looks acceptable as a form factor. So my conclusions are that it does offer a potential scaling path for an intelligent machine, at least up to something like a primate level neuron count and connectivity. But scaling up any more than that really will require some innovation in terms of the memory density. And lastly, I just wanted to add that as a first step in this case, we are developing a platform based on an FPGA implementation that's for the wafer scale. But we want to first run it as get a model that can be used as a development platform from FPGAs on a board to try and run these machine intelligence codes and really understand where the pain points and bottlenecks are. And we're hoping to get some results on this year.
Thank you, Arvind. Really cool. There are questions, I'm sure. Comments, ideas. Yes, Giacomo.
I was also, in this case, I was wondering how long it would take to upload the data to the system if you have to upload all the connectivity weights of a simulation you want to run.
Well, I think the idea here is that the system should be self-learning. So you clearly have to put something for input and output to connect it to the rest of the world. And there's some initialization that would have to take place. But the hope or expectation is that once that initial boot up happens, the system should be self-learning or continuously able to adjust itself.
So your title mentioned HTM, and you've talked about, Yul Winfrey, you've talked about HTM before, but I understand you've moved away from the specific Numenta HTM. How do you establish confidence that the numbers you're generating now will work when you actually have the algorithms worked out?
Well, that's the purpose of this third bullet point, is to develop an FPGA system. But I'd also really like to emphasize that we're not trying to develop an HTM machine. This is a very distributed processing system in which each processor has a lot of memory that's co-located with it. And it could be used or programmed for many different applications, but it's not intended to be HTM specific. The only place that I really used HTM in this analysis was in making some estimation of what a typical compute cycle might be, and whether the communication could be hidden behind that compute cycle. But other than that, I have stayed away from trying to make this a specific HTM application.
Thank you.
Okay, I see. Is there another question? Oh, yeah, okay. There is it.
Yeah, so you started off with the spec sheet, which looked like the Spinnaker spec sheet. And then you designed a machine which in many ways is very similar, okay? Clearly you're being much more aggressive with the technology.
Yes.
But nearly all the concepts here could be tested on the Spinnaker platform, right?
That's a very good point, and I had the temptation to get up here and simply point to your talk and say ARM processors, and point to Karl Heinz's talk and say wafer scale and sit down. But I decided not to do that. You're correct, there's a lot of overlap. I think one of the differences might be that we are really trying to co-locate processor with a lot of memory in this case, and cut those distances down. But as far as a sort of a testing prototype is concerned, I do see a lot of overlap. The only other sort of contrast I would point out is that we're not really focusing so much on a spiking neural network, and at least my understanding from your talk was that Spinnaker does utilize more of a spiking type of algorithm.
Yeah, Spinnaker's optimized for spiking networks, but people build other sorts of networks on it. I mean, the packet payload does allow you to model non-spiking networks and MLPs and standard deep learning and so on. No, we should compare numbers, because I think what you're proposing is a kind of scaled version of what we've got.
I would agree with that. Its intent is, again, to kind of move away from chips, the idea of chips on a board, and see if we can't actually put all of these things on a wafer. But I would agree conceptually, at least, because we are staying with CMOS. We don't want to attack too many problems at once, and so we're really only trying to attack the problem of getting big and getting to interconnectivity. I would tend to agree with that.
Okay.
Okay, so thank you again for the presentation.